So now let's discuss about hyperbola. So hyperbola, this is the one that extends through the base of one side of the cone all the way through to the base of the side of the cone, producing something that at first looks kind of like a double parabola. With its two separate branches, although the shape is actually quite different, the differentiation of hyperbola is similar to that of an ellipse, where there are two foci, except that while every point of an ellipse has distance to this foci that give a constant sum, every point on a hyperbola has distance to the foci that give a constant difference. The foci sit here on the outside of the branches. Then here we have the two vertices, and between those we can find the center, which sits on the transverse axes that connect the vertices. The equation for a hyperbola will be extremely similar to that of an ellipse. In fact, the only difference is that instead of a plus here, we have a minus, which makes sense given the difference between distances, the foci being constant instead of the sum. Everything else will be the same except that for an ellipse, we always put x squared first and y squared second, while the a and b terms could move around. This time, the a and b terms will stay put, while x and y can swap spot. If it's here x term first, the hyperbola will open up around the x-axis. If the y comes first, it will open up around the y-axis. The a, b, and c terms we know will mean pretty much the same things as well. A is the distance from the center to vertex and C is the distance from the center to a focus. One difference is that B is no longer means much graphically, and we will just use it to solve for A or C. And this time, the equation will be C squared equals A squared plus B squared. Let's try an example. Here is an equation in standard form, where A squared is 16 and the B squared is 9. A is the distance to a vertex, so the vertex must be at plus and minus 4. Then we do C squared equals 16 plus 9 or 25. So C is 5 and the foci must be at plus and minus 5. And that's enough information to do a rough sketch of the hyperbola. If the x and y terms were reversed, we would have a similar situation, except that now the transverse axis is vertical, but the distance to the vertices and foci will remain the same. Just like with ellipse, we can also be given coordinates for vertices and foci and generate the equation from that. Vertices on the x-axis at plus and minus 2 and foci at plus and minus 5 means that 25 equals 4 plus b squared, which makes b squared 21. So, our a squared and b squared terms go here. The x term comes first since it's horizontal, and that's the equation for the hyperbola. If you're having trouble drawing the branches of the hyperbola, one thing that can help is to draw the asymptotes. These are the lines that the branches approach, getting closer and closer but never touching. And for a hyperbola that opens around the x-axis, these asymptotes are given by the equation y equals b over a times x and y equals negative b over a times x. For a hyperbola that opens around the y-axis, the asymptotes are given by the equations y equals a over b times x and y equals negative a over over b times x. If you draw these asymptotes with dotted lines, this can help you draw the hyperbola a bit more accurately. Again, if a hyperbola is not in standard form because this number is not 1, we just divide 2 by that number to get rid of it. And hyperbolas can be transformed similarly to ellipses. If we rewrite as x minus h and y minus k, the point hk will be the new center of the hyperbola. That's what we need to know about hyperbola. So, that's all.